This lecture is an introduction to the idea of current, first of all, which I'll relate to you in an example of thinking about cars going on a highway. But then, really, this is meant to introduce you to some of the issues associated with electric current. So the current of electricity. So anyways, current. So current really is just this. It's the rate of the flow of something. And the thing can depend on simply what you're interested in. Some people are interested in the flow of water. Some people are interested in the flow of water within houses, or the flow of water in a sewer system, or the flow of water throughout an entire city or a state. Some people are more worried about the flow of groundwater, flowing through the sand and the dirt underneath farms. Some people are worried about the flow of water in the atmosphere, in the oceans, in the air, and in the ground altogether on the earth. So you can think about the flow of water on all kinds of scales. But water is not the only thing you can think of the flow of. You can also think of the flow of little particulate kinds of things. For example, imagine the flow of cars on a highway, and you can talk about the current of the traffic. So in this example, I've drawn a rough sketch or a diagram of cars moving along a highway, and you can see that the highway splits over here on the right-hand side. And I've just made myself a unit that's really descriptive and useful. And the idea is if you caused a person to stand right here and watch the traffic flow across, they're a traffic engineer or somebody that works for the highway patrol, what they will count, right? They just need a stopwatch and they just need to count. They'll count, say, for example, 4 cars per second. And let's say a different person is at a different place on the highway. If the traffic is even, that is, if there's no traffic jams or bottlenecks, then what you get is this smooth flow. And at this different location on the highway, you can also count the same number of cars passing by per second, so 4 cars per second. So let's say that a traffic engineer is standing over here instead, and they count 1 car per second coming along this piece of roadway. What would you say is the current that another person is going to measure? Hopefully what you're thinking is one scenario that could possibly be happening is cars are coming to merge on. This could be a highway on-ramp at 1 car per second, which is actually kind of a lot of cars, right? And they're joining a flow of cars that's already flowing, right, along this other stretch of roadway, and they're joining in at 3 coulombs per second. So I've got 1 coulomb per second, and I started to use the word coulomb, but I'm still talking about cars, and I'm not talking about electric charge yet. So 1 car per second coming, joining with at this junction, right? So this is a junction. So the 1 cars per second, 3 cars per second join, and they build up to be 4 cars per second. So 3 cars per second is a possible answer, right? And it must be that all these cars are flowing into the junction from the right and away from the junction on the left-hand side. And this speaks to a basic rule that you can use. You can say that the sum of the currents coming into a junction, so for example, here is some cars coming in and some other cars coming in. they're going to equal the sum of all of the currents out of the junction. So there's the into the junction traffic, and there's the out of the junction traffic. And this gives you equations, right? And equations are useful because you can use equations to solve other problems. Right? They're mathematical statements. They're quantitative rules with equal signs. You can do algebra with them. So here is an interesting comment. So up here, when I judged 4 cars per second, all this person needed to do was count and then divide by time. Right? And that's all this person needed to do. Everybody who's measuring a current on the highway only needs to measure this. So notice that although the speed must have something to do with what's going on here, right, on the highway, that's not directly what anybody's measuring. So nobody's measuring speed. They're simply just counting, like tick marks on a page. How densely the cars are packed must have something to do with something, but still, these people are not measuring the density of the cars. They're simply measuring the count of the cars per time, right? The current simply is still just a count and a time. So current is count per time. It's easy to get confused and wonder, why aren't we taking into account, for example, how fast the objects are moving, or for example, if the objects are slowing down or speeding up. None of the motion matters. It's simply just how many divided by a time duration during which you did your counting. Okay, so that's us thinking about cars on a highway, but the truth is electric current is precisely the same thing. It's the same set of details. Instead of cars, though, we're going to count coulombs. And that's why I was making the mistake earlier. Up here, this almost looks like I could have said 1 coulomb per second. And if you were listening carefully, I actually did make that mistake. But when I start talking about electric current, it's not a mistake. The electric current, which is referred to as with the unit of the ampere or the amp, or capital A is the symbol of the unit. The unit of electric current, the International System Unit, the SI unit, is called the amp, and 1 amp has the definition. It's 1 coulomb per second. Right? This is the definition of the ampere, which is the unit of electric current. Electric currents can come in amps. They can come in mega amps. They can come in microamps or milliamps, nanoamps, picoamps, right? You can use the Greek prefix and think about small amounts of current or huge amounts of current. The amount of current is what tells you about danger. It's current that kills people. It's current that heats up stuff as it passes through. Current is the dangerous thing. Electric field can be dangerous if it can flow a large current. Voltage can be dangerous, but only if a large current can flow under the influence of that voltage. Even really, really small voltage can be dangerous if a large current can flow under the influence of that small voltage. Okay, so this is a description of the units of current. right? You need amount of charge, or a way to count the electric charge. So coulombs is the SI unit of counting electric charge, and seconds is the SI unit of measuring time duration, right? The amount of time that passes. So in equations and formulas and in relationships, I'm going to use the symbol capital I to symbolize current, right? So some books use the symbol lowercase I, but I don't like lowercase I because it looks too similar to the imaginary number I. So I'm going to stay away from lowercase I, although that's what a lot of engineers tend to use, and also physicists and other scientists. I'm going to stick with using capital I. So I'm going to erase the lowercase I. So the symbol I, we're using it to denote a count of charge divided by a time duration. And this is one way to define the current. It's the charge per time. It's similar to up here when we define the current of an arbitrary thing. You just had to count the thing and divide by the amount of time it took you to count it, right? So this is the same idea, but Q, in the case of electric current, Q is electric charge. Delta T is a time duration. And that's what you can do to measure the current. But the truth is this current, as described here, let me see, this current described here is actually an average, because you're waiting a large scale amount of time and counting the amount of charge that passes in that large scale amount of time. So it is specifically, it's a time averaged current. But here, we're in this calculus-based class, and calculus can tell you about instantaneous values. For example, velocity is the instantaneous rate of change of the location of a particle. So the instantaneous value of the current is not this macroscopic count divided by a macroscopic amount of time. Instead, you imagine only spending really, really short time durations, so calculus limit dt, and you're counting the charge that passes by in those small amounts of time. And this is a really important definition in the case where the charge that's flowing might be time dependent, right? You can't depend on, for example, in the highway situation, that it's always 4 cars per second, right? Maybe at 3 a.m., it's only 1 car per 1 minute or something like that. And during rush hour, say at 7:30 a.m., it's going to be, actually, with a lot of traffic, actually, you might get a current of 0 because there's an accident that stops the flow, right? So that the current, that is the charge that passes by per time, can actually change in time itself. So, good. Let me give you an example of this. So here is a case of an IKEA parking lot. So this is the parking lot here. And IKEA parking lots have very strict traffic flow rules because they're trying to clean up the way that people can come in and park, right? So they often give you an inbound to the parking lot lane and an outbound away from the parking lot lane back to the street. And so in between the inbound lane and the outbound lane is the parking lot, and there's lots of ways to travel around inside the parking lot, right, depending on how large the IKEA parking lot is. And let's say that early in the day, when people are heading out to go shopping, you're definitely going to experience more cars per hour showing up than leaving, right? But later in the day, you're probably it's going to flip, right? Later in the day, you've got stragglers coming in, but close to closing time, people are beginning to leave, right? 15 cars per hour are leaving in a current out of the outbound roadway, and only 1 car per hour is traveling into the parking lot, right? So definitely the flow rate can have a different instantaneous value at different times, depending on the, the conditions, the, say, physical situation or the imperative people are feeling, right? Which is, it's close to closing time or something like that. Okay, so I want to revisit, though, as a last, let's see, is that the last topic? Yes, or it's almost the last topic. I'd like to revisit this junction rule. So earlier up here, we had this junction rule that 1 car per second is flowing in to join 3 cars per second, and those 4 cars per second are flowing out of the junction, right? We used this junction rule, which is an equation, right? Which says a definite thing because it has an equal sign, right? It's a definite prediction. So down here, what is the junction rule based on? The junction rule is actually based on a fundamental law of physics that the total amount of charge cannot change. Another way to say that is charge cannot be created nor destroyed. And that's similar, like we didn't actually think about it too much. Of course, cars are not created nor destroyed, right? The cars are coming in and the cars are coming in and they're combining and they're going out. None of the cars coming in are disappearing. And we're not, just because we're joining, the cars aren't being birthed either, right? There's no creation of a random car or an extra car. So the reason why we can say that the junction rule is this simple statement is simply because the object that we're paying attention to, that we're counting the flow of, right? Those objects can't just disappear, and new ones can't just show up out of nowhere, right? That's a fundamental statement for electric charge as well, and the junction rule is simply based on that conservation rule. So what this leads me to believe is this is sort of a simple junction in the sense that there is only one way in and only one way out. And if the flow in is bigger than the flow out, then it must be, because cars can't be created nor destroyed, it must be that cars are collecting. But that's what happens in parking lots, right? Later on in the day, near closing time for IKEA, more cars are going to be leaving the parking lot than showing up, which means that the number of parked cars in this sort of reservoir of cars is diminishing, right? So the junction rule is based on the conservation principle. It's based on the fact that the things you're counting can't just pop up out of nowhere, right? And they can't just blow up into oblivion either. Okay, so let's go and think about electric current. So electric current happens along conductors, along materials that conduct electricity. So these can include metals, but they can include other materials as well that aren't strictly metals. But all of the things that conduct are just referred to as conductors, right? When we're talking about electricity, electric current. So a wire is made of atoms, and atoms are little groupings of positive and negative charge. So a wire is a whole bunch of these atoms. So you imagine the wire just being somewhat of a tube, and the tube itself is made out of positive and negative charges. And the the point that I'm about to make is really, really important. Some of the electrons, actually not all of them, and you should read about that, some of the electrons are called free conduction electrons. That is, they can move around in our conductor. And they're going to move if there's an electric field that pushes on them, right? But actually, other electrons are stuck inside of interatomic bonds, right? So if I have a couple of atoms nearby each other, some of the electrons are actually responsible, for example, in metals, in metallic bonding. And those metallic bonding electrons, they are not free. If they were free, then I would lose the metallic bond, right? I don't want to lose the metallic bond because while the electricity flows down a wire, the wire doesn't fall apart, right? The atoms of the wire don't let go of each other. But let's say that you have 25 electrons that are in bonding. You could have 1 or 2 electrons that are free. And those are the electrons that I went and drew. So the electrons that I've drawn in here, the negative red signs, or the red negative signs, they're meant to be the 1 or 2 electrons per atom that are so-called free conduction electrons. But the nuclear centers, in this case, right, I have 27 electrons. Maybe I could have a nuclear center with 27 protons. And so this will be a little nuclear center of 27 protons and 25 electrons. But if you look at this thing, it's a net charge that's positive. So the nuclear centers, they're the little positive things, right? And they are stationary. If the wire is stationary, then the nuclear centers are stationary because the nuclear centers are the wire. Okay. So this is a basic model, and it's ultra basic. We're going to embellish later, right? We're going to talk about, actually, we're going to talk about a lot of things that I mentioned that we could ignore. We're going to talk about density. We're going to talk about the number of cars. We're going to talk about the speed of the cars, right? But in the case of this basic model of conduction electrons on a wire, we're not going to be talking about cars. We're going to talk about the density of the electrons that can flow. We're going to talk about the speed of the electrons flowing. Yeah. So here is the sort of last point of this small lecture. What happens if I put an electric field along this wire? So the electric field, I drew it in green. Do you see these field lines? They point towards the right, right? So the field points towards the right. So the force on the positive nuclear centers by this electric field is going to be towards the right. And the force on the free conduction electrons is going to be towards the left. Right? So, problem is, even though there is this electric force on these positive nuclear centers, the wire is actually held still by other forces as well. For example, like frictions and just simply the rigidity of the wire and the stability of the base that the wire is connected to. So the wire itself is not going to move, but the electrons move. And in this diagram, these little electrons, they feel a force this way, right? So they're going to flow. The electrons are going to move. Oops. I didn't mean to write that word twice. They move left, right? There is an electron current. And you can imagine, just like on the highway, Imagine a device of some sort. I'm going to draw it as a little person. All they do is they count per time how many electrons move past a certain location, right? So they're simply counting. And this little person is known as an ammeter. An ammeter is a device that measures electric current. So an ammeter. You might have wondered, why don't we call it an amp meter? I think it's just easier and quicker to say ammeter. Right. Okay. So here is a confusing point. And you're going to be confused by this for a little while, but at some point, you're not going to care about it anymore because you'll understand it. But until you understand it, you should try to work through your confusion. So, conventional current. Conventional current is actually, strangely, it's the direction opposite to the flow of electrons. If you read about conventional current, it's the flow direction of positive charge. But I just told you, positive charge cannot move as current. Positive charge is not flowing as the current. The flow direction of the conventional current is the flow direction of positive charge. Electrons flow in wires. Here's a diagram, something of a simple model describing that. And the protons and the neutrons do not, right? I argued based on the protons and the neutrons, and actually a whole bunch of the electrons as well, not considered free conduction electrons, but rather considered bonding electrons. All of those particles actually just stand still. Because the wire, if you look at it while current is flowing along it, the wire itself is not moving. So in the above example, right, in this example right here, the electrons, they are moving left. But the conventional current is opposite to the direction of the movement of the electrons. The conventional current is towards the right. A simple thing to remember is that the conventional current and the electric field direction, they're going to match, right? Because the electric field is pushing on positive charge towards the right. See, the electric field lines are towards the right. That's the direction of force on positive charge. The direction of force on negative charge is in the opposite direction. It turns out that the electrons are the things that flow, but because of a mistake made a long time ago and just simply naming which thing is called positive, the conventional current has been kept as the direction, labeling what's called the current. It matches the direction of the electric field.